Okay, hello everybody. Today I'm going to talk to you about a different type of permutation called a derangement. And before we get into that, I want to talk a little bit about permutations and how we can represent them in new ways. So for example, if I asked you to permute the set 1, 2, 3, 4, and just for simplicity, we're just going to write this as 4 in brackets. The way you might permute this set is just by writing out some ordering, 3, 1, 2, 4. And this is a completely valid way to represent a permutation. However, I claim that you can also represent this as a function as a mapping between two sets. And in other words, f of 1 is 3, f of 2 is 1, f of 3 is 2, and f of 4 is 4. And furthermore, we can take this function and transform it into a graph. And we have all the edges already. 1 is connected to 3, 3 is connected to 2, 2 is connected to 1, and 4 is connected to itself. So by the properties of a permutation, and by properties I mean we have a mapping that is a one-to-one mapping between these two sets, right? The functional digraph of a permutation is actually just a collection of cycles. So this is another way, a very helpful way we can think of permutations as just simply a collection of cycles. And a derangement is simply a permutation with no fixed points. So in other words, a derangement is a permutation without any cycles of length 1, or an element mapping to itself. So in the functional digraph representation of the permutation, each cycle has length at least 2. And we'll denote the number of derangements of the set n by dn. And I claim that dn is equal to n factorial minus this sum. And so how would we prove this? Well, when I see this expression, immediately what sets off alarm bells in my head is complementary counting. I notice that n factorial is simply the number of permutations with no restrictions of this set. And we need to subtract off all the bad ones. So a bad permutation in this case is a permutation with at least 1 fixed point. So how do we count all permutations with this property? Well, we're going to group by the number of fixed points. Let's call this k. So if there are k fixed points, the first thing we have to do is choose which k of the n members are fixed. And then we have the remaining n minus k members, which form a derangement, because none of them are fixed. And those can be permuted in dn minus k ways. Okay, so I hope this formula is clear. And let's take a look at another recursive formula, which is dn equals n minus 1 times the sum dn minus 1 plus the dn minus 2. So how do we prove this? Well, the key here is actually to do casework on the element n. So the first case is n belongs to a cycle of length exactly 2. So in our cycle representation of the permutation, n is in a cycle with some other member, and then the remaining n minus 2 elements form a derangement of size n minus 2. So we have n minus 1 ways to choose this member, which is in the cycle with n, and then dn minus 2 ways to permute the remaining members. And then the second case is n is in a cycle of length at least 3. And so for this case, this one is a bit more tricky. What we're going to do is we're going to start with an arbitrary permutation of this set. So in its cycle representation, it may look something like, maybe something like this. We have some arbitrary collection of cycles representing a derangement of n minus 1. So this is a derangement. And the key is that in a derangement, every cycle has length at least 2. All right, because we have no fixed points. And using this derangement, we're going to insert n. So how do we do this? Well, that involves first picking one of the original n minus 1 members. Suppose n is 9, for example. We're going to pick one of the original n minus 1 members and just insert 9 in between it. So 7 would point to 9, and then 9 would point to 4. Kind of like inserting into a linked list. So yeah, so how many ways are there of doing this? Well, first we start with an arbitrary permutation, and then we pick one of the elements where we're going to insert n after it. So in total, that's where we get this sum. Okay, so maybe as a final exercise for you to think about is see if you can find a closed form solution for dn. So I presented you with two recursive formulas for how you would compute dn, but see if you can think of an explicit closed form solution. This is pretty difficult, and as a hint, you may want to think about using the principle of inclusion exclusion. Yeah, thank you.